Professor El-Askary is from the Center of Excellence in Earth Systems Modeling and Observations from the Schimid College of Science and Technology in United States. His talk today will be based on Earth observation solutions addressing SDGs in support of key environmental challenges. Over to you, Prof.
Good morning, Dr. Bolain. Thank you so much for having me. I really appreciate the opportunity, and it's good to be here with all these colleagues. I really enjoyed the previous presentation by Professor Almeida. He did a great job, and it was quite an enlightening presentation about the ethical usage of data sciences and what it is doing to our world. As mentioned, my name is Hisham Al-Askary. I'm Professor of Earth System Science and Remote Sensing, and I also direct the graduate programs in Computation and Data Sciences here at Chapman University in California. Today I'm going to be talking a little bit about the usage of Earth observations and data sciences in order to address some key environmental challenges. And let me start by sharing my screen. I believe you can see my screen now.
Yes, we can.
Okay. So as I mentioned in the title, I'm going to be talking about remote sensing observations and how we can use the interplay between satellite observations and Earth observations in general, alongside with data sciences in order to address some key environmental issues. The primary global risk report that came out in 2019 that was discussed in the World Economic Forum, Davos, they highlighted the most important risks which are facing humanities. And number one of those risks was the weapons of mass destruction, and then followed by another four risks which are facing humanity in general. And those risks were all environmental related. Believe it or not, it was failure of climate change system, mitigation, adaptation, extreme events, extreme weather, and natural disasters. All of these were among the highest in terms of likelihood and impact. If you can see that chart on the right-hand side of my screen, you will see that the vertical axis is about the impact, the horizontal is about the likelihood. And you can see in that first quadrant some of these topics which I'm highlighting in terms of the highest impact and the highest likelihood of occurrence. You would see some of these green boxes, and green represent here environmental, and the others I'm going to show you the scheme for those other colors all around the chart. But if you focus here on the first quadrant, you're going to see a lot of green diamonds which are representing the environmental part. Here there's cyber attacks, following from the previous presenter, when social media is made, or when there is a kind of a preference, or you are forced to do something because of AI, or because of these platforms that he shared. So you can see that these are among the highest impact and the highest likelihood of occurrence. Water crisis, which is a societal issue, biodiversity, man-made environmental disasters, and so on and so forth. So there are a lot of things which are falling along the environmental sector, which can be seen as global risks. And you can see from this chart here that over the time we have been seeing that the environmental components have been increasing in terms of impact and in terms of likelihoods. Those global risks since 2011, you can see the colors were not that many greens, but towards the more recent years, you can see that more and more of these environmental related effects have been on the highlights. Extreme weather events, you can see about global climate change issues, and so on and so forth. So in the later years, we have been observing, and this is something that we are all observing in our daily life, where we have witnessed the increase in the magnitude as well as the frequency of the occurrence of different kinds of natural disasters. Earth observations has proved to be a very useful tool addressing some of these issues, and the Earth observations have been one of the most important tools addressing major three global agendas, namely climate change action, or the climate action, which is known as the Paris Accord Agreement, Sustainable Development Goals, and the Sunday Disaster Risk Reduction Framework. What I'm going to be trying to do here is to show you how Earth observations have been used in order to support the majority of these global agendas and does have a broader impact. So I'm going to be highlighting some case studies along the Sustainable Development Goals in order to make the point and to show how data science and Earth observations can be of benefit and use. Among the challenges that are facing us in terms of achieving the Sustainable Development Goals and the implementation of the 2030 Agenda includes missing data. One of the speakers today was talking about the data sharing and how people can work with data together, and this is one of the biggest issues. Complementary, non-complementary interconnections between different sustainable development goals, complicated varied problems in quantifying and monitoring indicators with within different national and local contexts, and difficulties in modeling indicators to monitor those SDGs. So these are among the four most important challenges which are facing us. And for that, you will see that there are a lot of different kind of taxonomies for those SDGs. If you are aware, there are 17 Sustainable Development Goals which have been identified in order to achieve better life for all humans. And along those 17 Sustainable Development Goals, we have 169 targets that are to be achieved, within or under the umbrella of those 17 goals. And in order to see how much we are approaching or how much we are achieving those targets, there are 232 global indicators in order to see and to review the progress of our work towards achieving those targets and overall achieving the 17 Sustainable Development Goals by 2030. And for that, those goals have been identified in different tiers. So there are tier 1, tier 2, tier 3, and each of these tiers have different kind of classification along the lines of the data and the methodology storage. Some of them are pretty mature, some of them are pretty are still at the initial stages of development. So there are a lot of different kind of taxonomies and as I mentioned, along those three tiers. So not all the countries are able to achieve or are not able to use all the different kind of indicators, because different countries will have different capabilities and different abilities in order to even be able to measure or to be able to assess how much work they are doing in terms of achieving those goals. And that's why Earth observations are being used for monitoring these goals and the targets and the indicators to track the progress, and so that we are able to find a way to help the member states and the different custodial agencies to make decisions, and of course, because it's an iterative process, so to make adjustments along the way. As I mentioned, there are different targets and different indicators, as you can see, and those numbers are a representation of specific indicators. It's a very, very comprehensive analysis of these goals and targets, what needs to be achieved. So this is a picture of the 17 goals that needs to be achieved, and you can see they are covering a lot of different kind of sectors, and all of them are targeting one thing, which is better life for all humans. Speaking about no poverty, zero hunger, good health and well-being, quality education, and so on and so forth. Not all of these targets or goals, not all of these goals are environmental related or have one way or another a relation with the environment, but a lot of them does. And this is what I'm going to be shedding some lights on today. So I'm going to be talking a little bit about Sustainable Goal Development number 6, which is about clean water and sanitation. Earth observation data has been observed to be a key for water resources monitoring, and you can see those specific indicators where Earth observations can actually be used to see water use efficiency, freshwater withdrawal, proportion of transboundary basin water cooperation, and so on and so forth. So I'm not going to go through all of these indicators, but I'm just trying to highlight or to make you aware of the process that we are working under. So this is one of the goals, number 6, and these are some of the indicators or the key indicators which we are using Earth observations. Another one, sustainable cities and communities, and also showing here specific indicators 11.11, 11.62, 11.1, 11.6. So specific indicators which are talking about air quality, pollution, fine particulate matters, urban population, living in slum area or or advanced areas, and so on and so forth. Another couple of goals that I'm going to be also shedding a little bit of light on: life below water, and speaking of marine habitats, and speaking of coral reefs, as well as life on land, speaking about mangroves and other different kind of vegetation products or through vegetation habitats. And also there are a lot of things which are related to affordable energy. So let me jump right away into one of those case studies that we have been working on: changing trend of water variables, groundwater recharge pattern in the Nile Basin, which is under the goal of number 6, clean water and sanitation. This is a map showing you North Africa and South Europe. And this is a picture that was taken from NASA, or NASA mentioned like in 2012 using a satellite which is called GRACE, showing you the gravitational anomaly. So this satellite is showing you all these dark areas are areas which are experiencing massive amount of droughts. And what you are seeing right now is like, one of the worst droughts in the past 900 years. So these areas are suffering really water issues and water problems. And as you can see here, those dark spots are representing the lack of the underground water storage. So we started looking into the Nile Basin, looking into the hydrological cycle, looking into different variables which are if affecting the hydrological cycle. Those variables that you can see here, this is water equivalent, the underground. This is evapotranspiration. This is precipitation. So here we are showing you like different variables or different parameters, and we are doing some kind of correlation analysis between some of these variables at different lags, lag 1 month, 2, 3, and so on and so forth, so that we can see how Earth observations can address specific indicators like change in water usage efficiency over time, level of water stress, and so on and so forth. And from these observations, we have been trying to compare different African countries. This is the whole Nile Basin watershed, but now we are looking into South Sudan, looking into Egypt, Sudan, Tanzania, Ethiopia, Kenya, and Uganda. And as you can see here, some of those plots are showing you a decline, big decline in the underground water. And this red curve represents the difference between the precipitation, the evapotranspiration, and the runoff. So the blue curve is a proxy for the underground water level, and the red is the difference between the other 3 variables. And here you don't see much difference. It's like, almost stationary kind of data set, but here you can see a big decline in the underground. You don't see a lot of recharge because of course, of the lack of precipitation in the case of Egypt, for instance, versus in the case of Kenya, where you can see here some incline in Uganda as well as in Tanzania. So you can see the difference, and this is kind of helpful because you get to know more about the hydrological cycle. And as I mentioned, this is just showing you the lags between different variables. This is an animation showing you the water anomaly, the water stress. So all of these red spots that you can see is the representation of the underground water stress, which is telling you, like, that we are living on a water planet, and unfortunately our population is increasing dramatically, but the terrestrial water storage anomaly is on the decline. And this is a case here for Saudi Arabia, and you can see how the terrestrial water storage anomaly is really declining, and this is not very good. And of course, this is not something that like people living in these areas are going to be appreciating. So we always have to be looking into different ways of acquiring water and overcome this kind of water stress. Speaking of artificial intelligence and data mining, we used some of these technologies in order to study like drought cycles, which are present at a global level. What you are seeing right now was a long-term analysis using 150 years of data over California, where we were comparing between two different decades, a decade where it witnessed a massive amount of rain because of El Nino cycle, El Nino precipitation, and El Nino is a global phenomena which affect California by having a lot of rain. The year 1997-98 was very known to be a very strong El Nino year on California. Year 2015-2016 was expected to be an El Nino year. Our analysis showed that it's going to be quite dry year. What I'm showing you here, two different lines. The dark line represents the forecasted from our new recurrent neural network model, and the gray line represents the observed. We did data learning for the first 100 years. We did validation for the following 25 years, and then we started doing our forecast for the last year only during the year 2015-2016. So that's why you can see here it was showing very good validation between our validation data set as well as the the forecast and the observation. So here you can see how much like the big matching, and starting at this point we didn't have observations because we were trying to project on the precipitation for California during that year, and as I mentioned, it was expected to be a massive El Nino year. But our model said, you know what, it's going to be quite dry. And actually, what we predicted happened, and our paper got published in the Atmospheric Research Journal, which is one of the top journals in our field. But look at that. This is the article history. The article was received March 21st, 2016, and it stayed under review for almost a year, from March until December. So the editors, this is a tier 1 journal, very strong, and the editor could not believe that our projections are accurate. So basically they held the paper until they see what's going to happen with the season, and actually it was proven to be quite dry, and the paper was accepted in January of 2017. So almost submitted the paper in March and it was accepted. But it's the article history is quite good to look into that. So that was very interesting. Another case study that we are talking about here is the sustainable cities and communities. I'm gonna just show very few case studies, very few examples on air pollution issues. Here I'm talking about the different kind of platforms, different kind of satellites that we are using in order to look into variables like carbon monoxide, the sulfates, nitrates, ozone, UV radiations, different kind of locations, and we are comparing these kind of satellite observations in order to see the impact. We can do this kind of work and analysis on a regional scale. You can see this is something called the MIRA to AOD distribution, which is maps obtained from Tropomi. Tropomi is a sensor on board of a satellite, and you can see these are the different kind of variables that we are detecting and showing those kind of maps. And here we are showing different kind of seasonal variability: December, January, February, March, April, May, June, July, August, September, October, November for UV, and for carbon monoxide, same thing applied for NO2 and for ozone. So here we are just trying to show you the difference, these kind of regional maps showing the distribution in different seasons, sulfates and aerosol optical depth, SO2 and AOD. Again, Earth observations can give you this kind of understanding, as well as we can do correlation maps in order to highlight the anomalies which are present between different kind of variables. Here I'm showing you the correlation between NO2 and CO between carbon monoxide and the UV, and between NO2 and the UV, all of them from July 11, 2018 until July 10, 2019. So it's an annual observation, and you can see here the different kind of countries which are having different behaviors in terms of those correlations. We were able to publish a lot of papers along those lines, which are targeting the good health and well-being, and as well as sustainable cities. And again, like, the idea here is to see how Earth observations can be used in correlation with either ground observations or ground robotic networks, where we are getting some ground measurements, as well as versus satellite observations. And all of these are specifically addressing some indicators like mortality rate, annual mean levels of fine particulate matter. So these are indicators which are present in those sustainable development goals. So Earth observations along with data science can be used in order to address such an issue. Life underwater, we looked into coral reef habitats in different locations of the world, but some of the science questions and the challenges that are raised when it comes to coral reef habitat includes water column correction. You want to really fix the issue of having a water column on top of the corals, so that you can get an actual observation of the corals. Pixel and reef heterogeneity, site-specific geomorphology, the temporal variability, the water turbidity, all of these are among the major challenges which are facing any kind of work related to coral reef habitats. So we start implementing some algorithms in order to do some kind of corrections for the water column, as well as for atmospheric corrections, because we assume that the atmosphere is a vacuum, so that you don't get any kind of diffusion or scattering for the sunlight from different kinds of particles in the atmosphere. So you have to take this into account before acquiring information about the coral habitats or life underwater. So this is just a layout of the methodology and the different kinds of equations that we've been using in order to do some corrections for the atmosphere, as well as for the water column, which is falling above of the water of the coral habitats. We looked into different kinds of applications, different locations. This is in Egypt, for instance, where you have satellite images. You do masking, so you remove the land component so that you focus only on the marine habitats. So you can see here the masked images. And we do intercomparison between different kinds of decades, 1987, 2000, 2013, so that over the time you can see the succession of the behavior of these coral habitats. You do supervised and you do unsupervised classification. We applied some ISO data and k-means clustering, where we had some end members selection here. So we know some ground observations, where we know some areas with those different kinds of habitats. We compared between those this island where we know the data exactly, and then we use the same kind of methodology and learning from that location where we had ground observations, and we applied on the whole region of interest, or the whole ROI, in order to see the advance or the change of the coral habitats from to over the course of time. And you can see here a satellite image showing you the area under study, 1985, and you can see the urban development and the impact of humans in those 3 decades. You can see the difference, massive change in terms of urbanization, which caused more stress on the marine habitats. This work was published and was really highlighted on the NASA Earth Observatory platform, it was selected to be an image of the day back in 2015. We started working on different islands present in the Pacific in order to look into in order to have a global classifier, so that we can address different locations worldwide in terms of coral habitats. So this is a case study where we used 4 different islands. As you can see, those 4 islands, we had ground observations from different domains, so that we can teach our models, we can learn from them, so that we can create a global classifier. So the idea here was to have satellite observations which are covering different time domains, different regions, as well as ground truth observations that you can use in order to educate your models We used neural networks. We used a lot of different kind of models in terms of deep learning and random forest and things of that sort. So a lot of these models were used in order to be trained so that we can have a better classification and probability maps, as you can see for these islands. So the assumption of the pixels where corals are present, and then see the accuracy of the model. So we had 4 islands that we learned from, and this is the area under the curve. This is the accuracy, as you can see, and this is here the correlation between, or the performance summary, if you will, in terms of accuracy between what was estimated and what was actually present. And then we use that, and actually, by the way, this also was published and was highlighted on the Landsat science domain with NASA as well. But we use that in order to apply to another 2 islands where we had no data whatsoever. So basically, we created a global classifier which is able to learn from these 4 islands where we had actual data on the ground, and then we applied it on another 2 islands where no data was available. And we were able to see very good outputs and results in terms of looking into the decrease in the coral cover by kilometers or by percentage. And you can see here, based on the change detection analysis that we did, we saw that there was a big decline in the coral habitats in these areas. What I'm trying to show here, what I try to show over the past few minutes, to show you some kind of products which are driven by science, things which can really address the 2 phases of sustainability that I'd like to call, where you have an idea, you have a business plan, but you come up with marketable products, observations that we can use in order to participate in having better life for humans, and how we can commercialize that, how we can expand that. Along this process of understanding, there are a lot of processing tools, data being used, incubation, funding, and acceleration. And this is what we see as a value chain, where you have the interplay, or where you have the relationship between academia, industry, and the government, so that you can have a better life for humans. And I'm going to leave you with those concluding points for you to read. Thank you so much for your time, and I hope you find this beneficial. Thank you so much.